Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it is my pleasure to introduce Léon Bottou. Léon is working at the NEC at present, and he's a machine learning guy. Léon has the rare distinction of being able to argue with Vladimir Vapnik about bound and convergence proof and actually win the arguments. And there are only a few people in the world that can have that claim. And also Léon is also, I would say, a Uber hacker. He did the déjà vu compression system, but anyway, today is going to talk about machine learning and learning with large data set. Thank you.
Hello? Oh, yes, it works. Okay. So that's a talk that's, in a sense, very similar to the tutorial I did in NITS 1 week ago. So I'll make some differences, and maybe I can try to give a slightly different bias. So some time ago, I started to be interested in large data sets, and there is something we know from experience that some algorithms like stochastic gradient, they're working really well, even though their properties are sometimes subject to discussion. So I started to think about large data sets and what we should do with these things. And so the first thing is to understand why we want to use large data sets. And I see two reasons. There might be others, like Sam Rowes has this nice spatial imaging or scientific imaging, but these are the two that are of direct interest. There is one is data mining, and it's clearly a money thing. You want to gain competitive advantages by analyzing the data that comes from our computerized society in all kinds. And that there is a lot of issues there, the privacy issues. This is a domain in which you might need large-scale learning algorithm. And another one that's, well, long ago, that was one thing I was interested in, is if you someday want to do artificial intelligence, and you might want to do that because if the planets keep heating, that might be the only thing left from us. Then you have to learn from data during the time you receive it. You don't get a second chance. So to look at the first problem, the data mining, suppose you have a society with just two kinds of computers. You have makers, they do business, they generate revenue, the people doing the work. And you have thinkers, they analyze the data to try to find a better way to find revenue. So when the population grows, the ratio of thinkers over makers must remain bounded. Otherwise, the thinkers get very hungry. And the data grows with the number of makers. And the number of thinkers doesn't grow faster than the data. So what does it mean in practice is that we have a big problem. That the computing resources available for learning do not grow faster than the volume of data. Yet, most machine learning algorithms demand resources that grow faster than the volume of data. If you take a matrix, typically you're going to have n-cube algorithms for n-square coefficients. If the matrix is sparse, then it's even worse. That means that as long as you design algorithms using matrix operations, so by summarizing using MATLAB, you're going to have a big problem. It's just in front of us, we're running into that. So the talk is going to have three parts. The first one, I'm going to discuss the relationship between statistical efficiency and computational cost. In the second one, I'm going to discuss stochastic algorithms. And there is sometimes a confusion. I don't say that stochastic algorithms are absolutely the best. I just say they're difficult to beat. And I think Shunui has some ideas about how to beat them, and we'll see. And the third one is going to be learning with a single pass over the examples. And this, I'm going to shortcut this a little bit and make it a bit shorter to have more time to go there. So the first part, and that's a joint work with Olivier Bousquet, and is now in Google Zurich, in fact. So if you read the statistical learning literature, all this stuffy theory that we had during the last 10 years of NIPS, you learn that it is good to optimize an objective function that ensures a fast estimation rate when the number of examples increases. That seems quite logical. And this is true. Yeah, the bounds that these people have derived, they're pretty close to, well, at least not the bounds, but their asymptotic behavior is pretty close to what's really happening. They pretty much nailed that part. If you read the optimization literature, you know that to solve large problems, it's good to have optimization algorithm with strong asymptotic properties. And that's also true. This is wrong. That if you put both together, well, use a superlinear algorithm to optimize an objective function with fast estimation rate is what you could think at first. But I won't show that this is wrong. So let's look at the baseline large-scale learning algorithm, which consists in randomly discarding data. So you have 1 billion samples. Well, you take 100,000 that you take more or less randomly. Well, that's a good way to handle large data sets. It works. And the question is, what are the statistical benefits of processing more data? And what is the computational cost? And to discuss this, we need a theory that discusses both statistics and computation together. And Vapnik theory does not discuss computation. Vapnik doesn't care. In fact, Vapnik doesn't care much about machine learning. It cares about learning in humans, in science, in plenty of things. And he cares about machine learning to the extent it can prove him right. I'm just summarizing, but there is some truth to this. Valiant in 81 defined something that's very close to Vapnik's theory. The only difference, but the main difference, I think, is that it excludes exponential time algorithms. But the problem is that exponential time is way too slow. Polynomial is too slow. Linear is what we need. So it's already a baseline that's too high, and there are very few results that will deal with that. So that slide is to show how messy the framework is. So who is familiar with the framework? Who is not familiar with the standard framework of machine learning? Okay, so
what do you mean by standard?
The VC kind of thing. Okay. Okay, I'll just go slowly. So the goal of this slide is to put all the math together to show how messy it is. So you assume that you have examples that are drawn independently from a distribution. X are the inputs, Y are the outputs. And that represents the rule of nature, and you don't know it. And you would like to minimize some cost. You find some function f that minimizes the cost. That's an expectation over that distribution. For instance, the cost could be whether your classifier f misclassifies some data, and you want the expectation of that, which is the number of errors you do on a hypothetical test set that's as big as you can. But you're in trouble. So you define the empirical risk, which is the average of this same loss on the examples you have on your training set. So this can be seen as an approximation of this. So what do you want? You would like to find the magic function, the magic classifier that minimizes the error among all functions. The thing that works the best on all future examples you've seen. And in general, well, this f star is something complicated that doesn't belong to the family of functions you're considering. So the best you can do is to find the best one in your family of functions that you choose. You choose some family of functions, let's say linear, the models you choose. You choose a model for a classifier. And well, you try to find the best set of parameters for your model. But this P is unknown by definition, because if we knew it, we could solve the problem. We wouldn't need learning. So instead, we compute the function that minimizes this empirical risk within our family of functions. And there is all this Vapnik-Chervodenki theory that tell us when this can work and how you can make it better and how you choose F and everything. So that's the standard framework. We have two big approximations. First one is that, well, you would like the best function, but you reduce your ambition. And the second approximation is that, well, you make sampling, so you reduce your ambition as well. So since we're reducing our ambitions, well, why computing this minimum exactly? If we compute this minimum exactly, we have to invert matrices, do things that are too costly. So let's assume that we return something that's within a row of the optimum. So for instance, you could stop an iterative algorithm earlier and so on. And a lot of things will be discussed by how you can scale this row with the number of examples. So when I do this, I can decompose my error. So this is the best error I can have on future testing examples. And this is what I'm going to do with my approximate algorithm. And this error can be decomposed in three terms. The first two, they're quite classic. The approximation error, that measures how much you lose because you use a predefined model, a predefined family of functions here. The second one tells how much you lose because you're using a finite sample. And the last one is a new one, is how much you lose because you don't optimize the stuff you should optimize. And the goal we have is to minimize this, that is to choose the model, choose the number of examples, and choose the accuracy to make this as small as possible. And usually, people say take all the examples, but in the reality, we don't have time to take all the examples. So this is why I put the number of examples and the accuracy in this thing. And I'm going to have two budget constraints. One is going to be the maximal number of examples. Another one, the maximum computing time. So suppose I replace this by estimates or formula that estimate what these things should do. I have an optimization problem. And since I have constraints, one or the other constraint can be active. Both can be active in some rare cases, but basically just one of them in general. So if I look how these things move, they move in a rather obvious way. Like the approximation error decreases when the family of functions gets larger. The estimation error decreases when n gets larger and increases when the family of functions gets larger. If I have more flexible model, that's going to decrease. The optimization error basically moves with rho, and we're going to discuss that. And the time decreases with rho, increases with n, increases with the family of functions. So that's pretty much the obvious movement you would expect. So I'm going to make two definitions. I'm going to say that we're in the small scale situation when the budget constraint that's active is the number of examples. And I'm going to say we're in the large scale case when the budget constraint is the computing time. So far, it's just a framework, but it's very easy to understand that we're going to be in one of these two situations. So the first one is a small scale learning. The active budget is the number of examples. So to reduce the estimation error, I can take all my examples. To reduce the optimization error, I optimize to death. And the only thing I'm left with is adjusting the model. And have this graph that you see in all machine learning publications in the last 15 years, where you have this trade-off between approximation and estimation error, and if you choose the right size of a model, you get the best performance. That's the easy case. A large-scale case is a lot more subtle. For instance, let's take an instance. If you choose to optimize more, well, it's going to cost you time. You're going to decrease the optimization error because rho is smaller, but you must also either decrease the family of function or the number of examples in order to fit in the required time, and this is going to have adverse effects on estimation and approximation errors. So this seems to be a complicated landscape, and it's true it is. But it's something very interesting because the trade-off now depends on the optimization algorithm, the one you choose. And this is, from a theoretical point of view, this is a good thing because now I can ask questions about optimization algorithm. Which one is best? Or compare them in a rigorous way. I can ask rigorous questions and give rigorous answers if I study in this framework. It's more complicated, it's true, but things can be done. Are there any questions at this point? Fine. So now that I have this framework, which allows me to ask rigorous questions, I just have to run the math. So you're going to have a few slides of math, and we'll see what kind of results we get. So, but before going there, I'm going to give you a summary of what's going to happen. So this is the log of the time, the optimization time, and this is the log of the accuracy. And typically, a mediocre optimization algorithm, like the one we often use in machine learning, they do something like this. So they're called to be linear, meaning that the log rho decreases like the time. So it's like, and if you have a good optimization algorithm, it's going to be super linear, it's going to be a bit faster. You could have very slow optimization algorithm where rho decreases like 1 over t. But if the best rho is here, the red one will win. Now we have to go to this math. So the first one is the estimation error. And there are plenty of results there, the uniform convergence bounds of Vladimir. And basically, this is statistics. In statistics, things decrease like 1 over square root of n or 1 over n, depending on how you set up the thing. It's between 1 over square root of n and 1 over n. And this is what says alpha is this coefficient. So if you look at the VC literature, you have at least 3 kinds of bounds. In fact, there is a 4th kind that exists, where you have the classical one in square root, some ones that gives you bounds in 1 over n, and intermediate things where you can make assumptions or study in particular loss functions that have better property with alpha somewhere between 1/2 and 1. And there is a big theoretical topic these days of finding setups in which you can make alpha as close as 1 as possible. So these are based on uniform convergence, meaning that these bounds, in fact, they're true in the complete neighborhood or in all the space, or in the worst case in the neighborhood of the optimum. So that means that if you make an error rho on the empirical risk, you can easily put it in the bound. And you get something like this, if you want to take into account the approximate optimization. And that tells you something very simple, that rho should not be much smaller than that. This is useless. And rho should not be much bigger than that. So that tells you basically the kind of order of magnitude you should have for rho. Now, if you want to add the approximation error, the choice of the model, so there are some results that give you bound when f is by lambda regularized cost, but the truth is that if you want to do that, that means also that we select the variables, we select features. And this is a complete hell, theoretically. So all this slide is there to say that I don't know how to say very meaningful things here, in my opinion. I could spit theorems, but I don't think they're very meaningful. So I'm going to consider f fixed. So now that we have the basic rules, let's take a fixed model. And I'm going to take function linearly parameterized by some w, just to be simple. Or you could make more complicated things, use more complicated theorems, and so on. So this is just an example. I think that optimization algorithm for learning should be studied that way. And I'm going to look at 4 of them. The gradient descent, the second order gradient descent, which is a Newton kind of algorithm, stochastic gradient descent, and stochastic second order gradient descent. I'm going to make a number of regularity assumptions, things are differentiable, everything, because I don't want to make my life too complicated. And there are some quantity of interest like the Hessian or the Fisher information matrix, and the main goal is to define some condition numbers, like there is one which is the trace of GH minus 1, that's depending on the loss function, that appears sometimes. And another thing that appears is lambda mean, lambda max, the eigenvalues of the Hessian and their ratio. It's just technical things. I'm going now to go over all the 4 algorithms and explain what the result is and what it means. So the first one is a gradient descent, plain, simple. WT, I take WT, I remove eta times the gradient, and I get the new one. So this is something, if I'm here in that paraboloid, paraboloid, I'm just going to zigzag to the optimum. And this has been studied completely. We know that the best speed is achieved with when eta is 1 over lambda max. And basically the cost of each iteration is nd, because here I have a sum of n terms, each one has dimension d. The number of iterations to reach a certain accuracy scales like log of 1 over rho. The time, that's just the product of these two. And the last column is the interesting one. I take this formula and I replace rho and n by the values I should use to reach a certain epsilon accuracy on the testing set. So I get a formula like this. I'm going to come back to it. You see that you have this, it's dominated by the polynomial term in epsilon here. And that depends, of course, of the estimation rate. If I take this and I say this equal T max, the maximum time I have, and I solve for epsilon, I find the best error rate I can achieve in that time, given all the assumptions I've made. There is a little thing, there is this O notation here, so there is always an abuse in the O notation. So I can tell you what's hidden in it. Here you have the cost of a single operation. Here you have the initial point. The initial point has some importance there. That's the product, and here you have some messy constant that come from the generalization bounds as well. So, yes?
Is this all assuming that the whole thing is equal to
No. It's just assuming it's twice differentiable. And just assuming twice differentiability in that case.
How can you get these things on an arbitrary function? I didn't follow that.
Arbitrary functions. But it just, you make a first order analysis and you bound the residuals.
But the eigenvalues are defined for the quadratic form matrix, so it is assuming the quadratic form approximation.
Yes, you make a quadratic form approximation, you make an expansion, you bound the residual terms, and you compute your speeds.
But you don't know the learning rate without the assumption and without lambda max.
Yes. I'm just taking the optimistic view. If you take a gradient descent, you're not going to be much better than that. Is what it means. You can always screw it up if you want. Yeah.
Well, it could be that the quadratic approximation, that the optimal place to stop isn't close enough to the minimum where the quadratic expansion or the minimum is there. Right? It could be something way to
This is why this is asymptotic. And a thing I should have been making clear that in order to simplify my calculation, I just look at the asymptotic point of view, because all the generalization bound I discussed before, the absolute value is perfect crap. What they nail pretty well is the asymptotic behavior. So when I'm
optimum time to reach that might be well before the asymptote.
this is what I can say.
I know.
You know,
On that slide you just showed us, this one here, where did the alpha appear? Because it didn't appear until the last column. Where does that come from?
this alpha, it comes from the estimation rates I get in these bounds. It tells you it's between 1/2 and 1. It tells you whether the statistical part of the problem is set up in a way that you get a convergence of the error in 1 over square root of n or 1 over n. And you can, depending what loss function you optimize and what assumptions you make on the data, you can have bounds that go in 1 over n.
Okay, so it's dependent on the loss function.
It's depending on the loss function, or this kind of Tsibakov variance conditions are things you can assume on the data. Like if the separation between classes in the classifier are quite neat, you can have better speed. And you can exploit that to make algorithms that learn faster with the number of examples. You know that, and dealing with this alpha, it has been a big topic in the theoretical community in machine learning. So you have all these pages and pages of paper by Bartlett and Bousquet and Audibert and others that look when you can get a good alpha, because it seems to be a good idea.
It's a literature I'm not familiar with, whereas everything up to there is just standard numeric analysis.
It's completely standard. The machine learning part, you have this alpha, but that's basically statistics. You know, if you average things, you have an accuracy in 1 over square root of n. And you know that if you do smart things like getting closer than student t-test and things like that, you can go over 1 over n in some cases. And getting this in machine learning seems to be a good idea. But it won't be, you'll see later. So if I replace my learning rate by the inverse of the Hessian, I get basically a Newton algorithm. And I'm going to be very optimistic, assuming h-1 is known in advance. I don't have to compute it. But still, the cost per iteration is higher. I have to multiply a matrix vector. The number of iterations to reach rho, now it's a log 1 over rho instead of log 1 over rho. So it's a lot faster. Time to reach a certain accuracy, asymptotically a lot faster. But if you look at this, you replace rho and n by the right values to reach a testing error epsilon as fast as possible. Well, let's compare. Looks the same. You know, you have a log that one of the log became a log, but still dominated by this term here. And basically, you're not learning much faster. You're optimizing much faster. You're not learning much faster. Well, you remove the condition number. You made some changes in the constant, but it's a bit disappointing. Let's go to stochastic gradient algorithm. You draw a random example at each iteration, and you correct W by just the gradient with respect to that example with a decreasing learning rate. And basically, you have a very noisy estimate of the gradient. On average, it's the real one, but you have a very noisy process. And what's happening is that when you're close to the optimum, you're still hovering above the optimum in a kind of radius that decreases with the learning rate. But you cannot decrease it faster than 1 over t, otherwise it doesn't converge. So this has been studied as well, and the best decreasing gain is with eta equal 1 over lambda mean. Cost per iteration is very low, order d. Iteration to which row? They're in 1 over row. That's very slow compared to everything we said before. And you notice that the big O is gone because we don't even care about the initial value. The thing that limits the speed is the noise I'm going to have in the final part of the convergence. So the time to reach a certain accuracy is hopelessly long compared to the other algorithm. But if I replace rho by the right values, actually it's the best one so far. So there are several things to notice here. First of all, it's again in 1 over epsilon, the polynomial term is there, but I don't have the log terms. The alpha is gone, meaning that this goes as fast as if we had the statistical estimation rate in 1 over n. That looks very surprising. You know, all this work on finding better bounds, is it wasted? Well, here is what's happening. Suppose I'm in a crappy case where the thing converges in 1 over square root of n. It means I don't need to optimize as accurately. It means I have time. I have time to see new examples because I assume I'm bounded by the time. And overall, it cancels out. So if you have plenty of examples, some problems just go away. This is quite a good news.
I'm a little confused about lambda min.
Yeah, lambda min of the Hessian, yes.
Yeah, I understand lambda max, but lambda min, if I had a weight that was not connected to anything, lambda min would be 0.
Yes, because I assume that you have a single optimum and that weight make a lot of optima.
Right. So it's not really lambda min, it's some lambda in the
Yes, correct. You can refine that in that respect.
Okay.
You know, I'm just making a very simple analysis. You're absolutely correct. You can refine the effective lambda mean is going to be something else. And if you're not in the asymptotic case, you sample at big things. So even if it's non-differentiable, because the learning rate is not 0, they're going to be an effective lambda mean. You can make crazy mathematics on it.
Well, actually, we probably can't. But it's the smallest lambda mean that matters, I guess.
Yeah. No, you can make crazy mathematics about it. It's just boring.
Okay.
So Neil, this actually almost could be a square of the condition number of the Hessian.
Well, because my bound sucks.
But even then, that tells you that it's, in fact, something that's in practice, that it's very, very important to condition your data if you do stochastic.
It's very important to condition your data if you do stochastic. And you'll see that basically the difference between stochastic and the best thing you can do with batch and batch method is, well, you have the log terms, but they don't care so much really. It's new constants. Engineering matters.
And nu is even worse, right? I mean, the nu is the other thing.
The nu is in many places. Nu is not big. If you take something like a log likelihood, nu is going to be 1.
Oh, but this is also for purely linear optimization, right? You're not doing any length functions. Well,
if you have a tweaky link function, nu will increase a little bit. Nu depends on the loss function, but not in a way that's catastrophic. But you know, if you compare the thing here before, in this one, you have a d square here. And you have the condition number as well. Even in Newton, you have a d square. And in the stochastic, you have a d nu. If you go to second order stochastic, you use the Hessian inside. You remove the k and you get a d square. But you just change the constants. So using second order stochastic is going to change the constants. You lose because iterations are more expensive, and you lose quite a lot, in fact. You gain the condition number. So preconditioning your data could do it, in fact. So at this point, what did I show? I show that it's possible to study the efficiency of optimization algorithm as learning algorithm in a rigorous way, provided you take the large-scale setup.
The thing you said about preconditioning, right?
Yes.
Made me think that the matrix multiply is ordered D if it's not a diagonal matrix, but there's that sort of simple form of preconditioning, which is just scaling.
Diagonal preconditioning is a good idea. It's part of your duties.
Right.
It's not something you should avoid. It's something I didn't do in the rest, actually, to show my point. But if you do something reasonable, you should do diagonal preconditioning. It's
and then you don't get that extra factor D, but diagonal
well, if you do diagonal preconditioning, this K just drops down considerably. And it's part of your duties. Or our duties, I should say. Even though I took some freedom with it in the rest. So at this point, that's a theory that suggests that stochastic gradient is very competitive. It didn't prove it's the best at all. It just proved that it's quite interesting. Yet, many people associate stochastic gradient descent with trouble. And if you ask, in the past, people were saying about only Jan can do it. And then Jan says, what about Mike O'Neill? You don't know Mike O'Neill, but I just don't have Jan's slides. It's a very nice one. You just search on the web for Mike O'Neill and convolutional network, and you'll see a nice little Windows program that's doing convolutional network, and then investigate who is Mike O'Neill, because you probably don't know Mike O'Neill. And it's very interesting. But now people just say, oh, okay, well, the question is whether SGD in backpropagation is difficult because multilayer networks are difficult, or because SGD is difficult. So the idea here is to try plain stochastic gradient on simple learning problems. And I took two like support vector machines and conditional random fields because there were these two papers recently in ICML, in two ICMLs, that were doing things very close to stochastic gradient with a little extra. And you know, nowadays you cannot publish a paper saying, oh, I invented stochastic gradient, because that was invented in the 50s. So everybody publishing a paper has to add a little extra. So I just took simple stochastic gradient programs for support vector and conditional random fields, and I removed all the fancy crap. So what you're going to see is plain, simple stochastic gradient descent. No trick, no diagonal conditioning, no nothing. I did the reasonable implementation. I'll discuss that a bit later.
All of the analysis up to this point for linear models?
It's for linear models, but you could scale it to nonlinear models if you wanted. It's just because the bounds are a lot more developed for linear models than nonlinear models. It was much nicer to use existing results than trying to prove our stuffy things in a corner. You know, what I'm saying so far has been quite general. So let's look at text categorization with support vector machines. So I take the RCV1 document. I have about 800,000 training examples, 50,000 dimensions. I minimize, I want to make a classification program, a simple one. And I minimize the cost that has a regularization term and a loss term. I just put them together in the sum so I can do stochastic updates on all this stuff. So the update is something like this.
That's just the margin perceptron with a little bit of regularization, right?
Yeah, it's a margin perceptron with a regularizer. I can do stochastic updates on this. It's pretty trivial. So some results. If I use the hinge loss of the regular SVM, and I use this value of lambda, which is not very good. It actually sucks. I used that one because it was used by Thorsten Joachims in some papers, so I could calibrate on what he was doing. So if you take SVM Lite, which is a typical SVM program, it takes a little bit above 6 hours to reach this primal cost and this test error. And Thorsten has a much nicer thing called SVM perf that optimizes for linear systems. So it used the fact that this is linear, plus some nice cutting plane trick, and cuts that to 60 seconds, which is pretty good on this number of examples. And it's not bad. The stochastic gradient is 1.4 seconds on that thing. And you get primal cost comparable and test error that is comparable. Now, if you take a log loss classifier, so that's interesting because now it's all differentiable, and instead of using these optimizers, I can use this thing that's from Chi-Jen-Lin, the liblinear thing, and this stuff is really good. It's a nice superlinear optimizer that does Newton updates in high dimension. And that's between 30 and 44 seconds, depending how you set the accuracy. And on that problem, the stochastic gradient with this lambda, which is a lot better, is on 2.3 seconds. So what's going on here? So here I have the accuracy, the raw I'm going to use, for both liblinear and stochastic gradient, and the training time. That thing is superlinear. You see, to get one more digit of accuracy, it needs less and less time. And that thing is awfully good. In less than 1 minute, it's going to give you 10 digits on the error. That's really a nice program. The stochastic gradient, boy, starts fast because it's so easy at the beginning, and at some point it hits a wall. You know, there is no way you can get more than 8 or 9 digits on this. The thing would die. 9 digits would be something like days, 10 digits would be years. Now, if you look at the testing cost, the same loss function measured on testing set, well, you reach the asymptote long before you hit the wall. And the points I was reporting were this one, and this one. That's the default in liblinear. So in fact, to use liblinear on log loss model, Chigen is setting an accuracy, because that's accuracy that works well, that stops liblinear well before its superlinear optimization starts to play a role. And at this point, the stochastic is just there much faster.
Yeah. And how sensitive are the time results in the previous slide to the choice of lambda, the initial one?
Well, I'm going to give you some point because this is a crappy lambda. This is a little bit better with a different loss. But Patrick Hafner tried this one with adjusting the lambda properly. And I'm going to give you the number later. Actually, that's here. So I put that on the web. These programs are on the web. You can get them from my webpage. They're very simple programs, a few liners doing stochastic gradient. And I got a mail from Patrick Hafner in AT&T, so he tried some and he sent me some results. So Reuters had the same problem, but he did the lambda right. And he was using libSVM with a sparse dot product of his cooking. That's quite smart. And that's slow. That's his nice SVM implementation with a lot of very hacky tricks. That's a lot faster. And SGD does that in 7 seconds. And Patrick told me in about 5 to 10 iterations on all this problem, I'm okay. So this is a translation where he took 1 million example for training, 250,000 features. It's very sparse, 7 seconds. And the other ones, it's the same kind of thing. I assume they're the same error rates. This is what Patrick sent me. He told me these all do the same error rates. These are all comparable. Now, then Olivier Chapelle sent me, hey, you're not doing what you advertise. You're trying to run this batch algorithm all the data. This is not what you advertised. You should try to run them on subsets of the data and find the right subset size. Well, he's completely right. He's completely right. So I did a Chapelle graph because he showed me that you can do this kind of graph. So here you have the training time, and this is the test error. So the stochastic goes like this. If you take 10,000 examples taken randomly in the set, you have the curve like this and the asymptote at this level because you have just 10,000 examples. Take more, asymptotes a bit lower, more and more. And that shows that if you want to learn in 1 second, well, you could just take 30,000 examples and you get this reasonable result. So you can do 1 second with a batch algorithm, taking less examples. And that's reasonable to see that because if you look at the theoretical results, they don't show differences that are so huge as the one before. They just say, well, you know, the order is pretty much the same except for the alpha thing, and constant change, and you have some logs that play nasty roles in the batch. Well, you get rid of the logs, stochastics is a bit faster. And if you think about it, there are 2 difficulties. If you want to do batch, you have to find what is the right size of the set you should use. And I don't know how to find the right size in advance, you know, by making small experiments. If you do stochastics, you have to choose the right learning rates because you don't know the eigenvalues of the Hessian. But I know a way to do it in a rather simple way. So I would still use stochastic. But clearly, Olivier is right. You know, this shows that it's not clear that stochastic is the best. Maybe there is another trick. So I tried again on CRF. So I take the chunking task, the classical one. This is interesting because there's a lot of parameters. And I used the plain SGD, so I just re-implemented all the things. This is the CRF++ program that you can find on the web. And this is my implementation that's compatible with CRF++, but I redid everything because I found it was too crappy inside. So, well, you go 10 times faster, basically. I didn't do diagonal preconditioning there. I didn't do anything.
Did you measure the log loss on the test? You're doing F1, which is 1 point in the RBC.
That's the primary cost.
That's on the training. You do the test log loss.
Yes, I have it. I can get it.
Are they comparable? That's the other thing, is that you have accuracies. And I'm wondering if it's good at that 1 point of the ROC, but maybe not so good for log. I mean, I think they'll be close. My prediction is that SVD
let's see, log loss on the test, 4,000 something. There is the log loss and the objective multiplied by n, you know, because here you have the regularizer. And the batch thing, what do I have? No, I don't have the log loss. I computed it at some point, I know. But I don't have it here. I'm sorry, I don't have it here. I was too... Well, the thing is that this could be made faster. Diagonal preconditioning would do it. This is really, if you look at the program, it's absolutely trivial. And this CRF program is about 10 times smaller than this one. So, as I told you, the difference in testing set efficiency of all these algorithms is pretty much in the constant or in the logs. So engineering matters. So the first topic is choosing the gain schedule. So I did something like this, eta over t plus t0. And I'm going to explain why. So if I look at the asymptotic theory of stochastic gradient, the key factor is 2 eta lambda mean, the lambda mean that matters. If this is less than 1, then you get a very crappy convergence. If it's more than 1, you get a faster rate. That's in 1 over t. And this is how you find that the best lambda mean, the best eta is 1 over lambda mean. So I want to be in that regime. So the first thing I do is I use eta equal 1 over lambda. Lambda is the regularizer, because lambda is less than lambda mean, and that ensures I'm going to be here. I'm not going to be at the optimum, but quite. Now, if you do that and don't use a t0 here, you observe that eta over t at the beginning is awfully large. So the bad idea would be to reduce eta. If you reduce eta, you go into that regime, and the thing sucks. So the good idea is to add an offset. So to compute the offset, well, I just made some back of an envelope calculation, knowing the expected size of the weights and the expected size of updates, and say, I would like updates that are comparable in size to the weights I'm going to obtain at the beginning. So in the CRF, my back of the envelope calculation, they were not so easy to do, so I used the secret trick, which is not so secret. So the secret trick, that was for the NIPS guys, because they claim that stochastic gradient is difficult, so you need a secret trick. The secret trick is that the sample size doesn't change the stochastic gradient mathematics. The n doesn't appear in the convergence speed. So at any moment during training, you can pick a small subsample. In the case of the CRF, that was 1,000. You freeze your weights, or you save them somewhere. Then you run your stochastic gradient with some eta on that thing. Fine, you see the result. If the cost increases, that means it was too large. If the cost decreases, that may be good. And you try several. You find the one that works best. You divide by 2 to be safe. And you use that for the next 100,000 iterations on the full set.
Training cost? Do you look at the training cost if it goes up or down?
Yeah, I looked at the training cost, but I could look at the testing cost. In fact, looking at the testing cost would be smarter. But so the CRF code I...
So fast, you just run it all from scratch. Forget about batches or anything. It only takes a second anyway, right? So just run the whole thing from scratch.
Well, the CRS is a bit longer. The CRS is a bit longer, but you could play that.
This is essentially an optimization of that.
Well, come on. This is true for everything. You have a big network, a big whatever stochastic gradient. You adjust your parameters for stochastic gradient convergence on small data set, and that's basically work on a large one. Yes?
So you're saying 100,000 iterations on a full data set, but how many problems with large data?
No.
No, 100,000 steps.
100,000 samples. Yeah. Yeah. So that's so there is some engineering matters. We're fighting on the constants here. So if you do this linear SVM, this is text, this is quite sparse. All these programs, the SVM programs, they've all been optimized for sparsity because SVM for text has been done a lot. So you have an update like this that you can split in 2 parts. The first one, you have the gradient of the loss, and that's basically is a very sparse vector. There is a 1 for each of the words that appear in the example X. So that could be very fast. You just hit a few of the coefficients in W, and that's it. Now the scaling can be costly because you have to touch all the coefficients in the weight vector at each iteration. And you make a lot of little iterations. So there are two solutions. The first one, I found that in Shalev-Schwartz. I say, my God, this is so simple. So you represent the vector W as the product of a scalar S and a vector V. You do update 1 on the vector, and you do update 2 on the scalar. This is exact, and this is damn fast. The solution 2, which is the kind of thing I would do, and if you do diagonal scaling, actually solution 2 is better. Because if you do diagonal scaling, the scalar is becoming a mess. As well, just you perform 2 with a lesser frequency and a higher gain, and you compensate. There is an easy way to compensate. And I tried both just to be sure, and they work exactly the same.
2 is simpler.
Well, in 2 you have to adjust the frequency of the frequency ratio. You have to play a little bit of measurements on sparsity. Well, but even if you learn the trick, learning the trick plus SGD is faster than running the SVM. Okay. But this is just engineering, you know. Engineering is important in learning. And this is something that I think has been lost in the last 10 years of NIPSS. And it's provably important. So I'll skip that to save time.
I have a question about constraints on your problem. Because for some kinds of problems, you can, if your number of constraints is small, even one per data point, that might not be so bad. What about problems where you have constraints that link all the data points together? Where,
that was unconstrained, all this.
Yeah, these were unconstrained, no, I know. But what about problems in which can you still get a win from SGD kind of approaches, or are you just stuck?
I would guess yes. I don't know. I cannot tell you this because I didn't study constraint problem. But if you take a constraint problem and use barrier functions, you basically make it an unconstrained problem, and then you can play with the barrier. It's becoming hacky again, but you can do it.
That tends to ruin the condition.
Yes, that's correct. And you can also see that when my speed analysis, it exists, it works when everything is nicely differentiable. If you have L1 or non-differentiable losses, then the speed analysis argument falls apart because lambda min, lambda max, they don't mean anything in that context. So you have to do smarter things again. So, I just discuss in a sense, a very general setup, but also a very simple setup. Because in that setup, I can say things. So this was just to show that, the example I showed before, they're toy problems. My SVM on Reuters or my CRF on chunking, they're completely toy. So I wanted to give that example because that's a rather old one. And also because I can take a little nap by saying that CRF was actually invented by Chris Burgess in '94. So suppose you want to do a check reader. The example is an image of a check, an amount. An amount is a number. It's not a string of characters. It's just a number. There are many ways to write the same amount. And there is a lot of engineering to do. We know that we need to find the fields, find the characters, recognize the characters, and so on. So we can define a lot of little differentiable modules all the way that do everything. They have to be differentiable so that we can compute gradients. Sometimes you have to do smart things in between, but that's details. Now, because it's a real problem, labeling data, it's expensive, but not so expensive. So you can label data. So you take little examples, and you get a labeling that's quite rich inside. And you pre-train modules with unlabeled data, small amounts. Then you put them together and it almost works. Actually, it works quite okay, in fact. You define a global cost function. In that case, that was the CRF after the seminal work of Burgess and Dunker in '94. And you train with stochastic gradient for a few weeks. That was done 10 years ago. It's been working for 10 years. But that's non-convex, non-linear, nasty. And there was no way we could have done that 10 years ago with sophisticated optimization methods. Had to be stochastic gradient. What time is it? Oh, I've been slower. I keep going, okay. Yes?
That's not convex.
That's not convex because you have a little thing. So basically, weights that are here multiplied by weights at this level, multiplied by weights at the level. So it's a complicated hyperbolic geometric. topology. The recognizer here are big convolutional nets with about 7 layers. So this is quite a deep system. It's not trivial to train this. And I'm not going to say that this time you're going to learn the trick very fast. It took some time to be able to do that. But if you really want the results, I think this is what you should do. So the last part that I'm going to shortcut a little bit is the learning with a single pass over the examples. And I'm just going to go over 2 basic results. So why learning in a single pass? Well, sometimes there is too much data to store, or sometimes it's stored in a very deep basement where it's just too costly to go and bother the people who are just storing it. So it's related to streaming data, tracking non-stationality, novelty detection. There are plenty of things to say here. I'm just going to be quite simple, and I'm just going to look at this first thing here. So when you add an additional example, you're basically changing the expected risk by adding just one little term. So you make a small change of the cost function. Small change. A small change, you can do first order analysis. First order analysis, the empirical optimum for n plus 1 example is the empirical optimum for n example minus some 1 over n, the gradient of the example you had, the inverse of some approximation of the Hessian, and second order terms. If you compare this with the second order stochastic gradient descent, this is awfully close. And the question is, could they converge at the same speed? So the answer is yes, they converge at the same speed. You can prove that thing, you can prove it in the weight space or the cost space. So basically this, I take the first one here. This says that the distance between the empirical optimum for n example and the best one you can find, which is the best generalization error, times n, is equal to the distance between what you do after t steps of second order stochastic minus what you would do at the infinity, which is the same thing. And it's a constant that you can calculate, in fact. It's just calculus. And you can do the same thing for the error. So let's see here. You start from here, let's say a starting point, and you compute the empirical optimum for various sizes training set, and you eventually get a W star n here. Or you can do one pass of second order stochastic gradient. Just go once over the data and find the Wn here. Now and this is the best solution you could find, the one with the best test error. This distance and this distance, they both decrease in k over n with the same constant, which is quite fascinating, meaning that this is going to be as good as this for the testing. For the training set, it's going to be different. For the testing, it's going to be the same. So that means that one pass of second order stochastic gradient is the same as making you full optimization from the point of view of the test error. So I hammer it. Given a large enough training set, a single pass of second order stochastic gradient generalizes as well as the empirical optimum. Experiment on synthetic data just to be able to push it to ridiculous accuracies. So that's a 19-dimensional stuff made out of Gaussians and the classification problems. I did that a few years ago. And the red one is the empirical optimum. The blue one is the stochastic gradient. This is the number of examples, and this is how much more than the best mean squared error I achieve on the test set. And they're exactly on top of each other. Now, if you look in time, well, the blue one is a bit faster. So if you do the blue one right and the red one right, they're very close. So the step you're going to do in the stochastic gradient, they're going to look like one Newton iteration. And you can use the Woodbury formula to use everything right. So the result is that to compute the empirical optimum, you pretty much do the same thing, but you iterate several times. And when you increase the accuracy you want, increase the number of examples, well, to compute the optimum, at some point you need to make one extra Newton iteration over the previous one. And every time, you basically lose something. So unfortunately, it's not so simple. Second order SGD is actually quite crappy. You must estimate this matrix H and store it. It's D by D, it's big. Even if your data is sparse, it's not going to be sparse. At each iteration, for each example, you must multiply the vector by the matrix. So the constant you lose is big here. So there are some research directions like limited storage approximation of H-1, reducing the number of epochs, diagonal approximation, online BFGS by Schraudolph is quite a thing I find very cute. But it's still an open topic. There is a little digression that this gives you a stopping criterion for stochastic gradient descent. So look, time to reach a certain accuracy, second order SGD nu over rho, SGD k nu over rho. K is this constant that we have. Number of epochs to reach the same test cost as the full optimization, 1k. Well, now that's very easy. Take your big set, carve two smaller sets, disjoint, train on the first one, test on the second, find how many iterations of stochastic gradient you need to do to reach the best test error on the second one, and that's k. Now you know how many passes you need to do on your big set to find your result. And this is very simple. Well, if you take too small, it doesn't work, but on large sets, it gives you the right order. If you want to be safe, do 2k and you're fine. So, okay, well, that's it. So, conclusion. I showed you a connection between statistics and computation by properly setting the problem of large-scale learning. And I show that you have qualitatively different trade-offs for small scale and large scale. You're not going to use the same algorithm. It's going to be different. I've argued that plain SGD is a good algorithm in both theory and practice. It's going to be difficult to beat. I don't say it's impossible, I just say it's difficult. But I say that you can do one-pass learning with second-order SGD, but the current algorithms are still slower than plain stochastic gradient, but that could change. And there are a number of topics of large scale that should be addressed and that this doesn't cover at all. That's it. I wish. This has been studied. In fact, there is this guy, Martin Moller, long ago, was using conjugate gradient on mini batches in stochastic processes and had some result that could work.
And I'm specifically talking about mini batches that are for cache awareness, right? So you're doing block multiplies, so you're really getting rid of that cost. Like this 5 multiplies is free for the cost of 1.
Dennis, you're right.
And I'm just wondering, what is the difference right now? You were saying it's slower.
Well, the D by D Hessian matrix is a pen. If you make mini batches, I don't know. I didn't do mini batches in a long time. I tend to work by conditioning by hand, the diagonal things, and I'm finished.
What I'm trying to ask is, what's the difference? Is it worth looking at?
I don't have figures.
No, but you have done second order, and you have done normal gradient.
You want to see the formulas?
Yeah, I'm just asking, how much slower is second order from first order? Is it 5 or less? So there's a chance.
Okay. The nu is the same. You have dk here. And here you have d square nu. So basically, if you can precondition and make k smaller than d, then it's not worth doing second order. Making k smaller than d, if you do diagonal approximation, you start to get close. But on the other hand, here I assume that you'd multiply by the Hessian. You could do smarter things. You could just use the first top eigenvalues of H and just use a few vectors. You try that, I think, at some point. And so you could reduce this cost d squared by d some constant. And if this constant goes to d, you have a d square here, but you have a continuum in between.
I can tell you, engineering is important, but there's a point where the cost of engineering is not worth the...
I understand. That's exactly what I'm asking. What is the gap? All I'm asking for is a number.
Well,
Gradient descent 5 times as fast as second order for your experiment you did, or is it 100 times faster, so the engineering's not going to happen?
Well, it's doable. If you can store the Hessian matrix properly, the thing is to look at, for instance, the best one I know so far doing something close to second order is the thing of Nick Schrodolph, the online ABFGS thing. And that thing is going to compute about the 10 or typically 10 highest eigenvectors of H using online limited storage BFGS. And it needs an extra pass to to compute the H-1 and update everything and so on. So basically you're looking at something that's on each iteration is 10 to 15 times slower than stochastic gradient for each iteration. But that thing, if it's right, is going to go in one pass. Maybe a little bit less because 10 might not be enough. That means that if you get the full convergence in 10 epochs, which is common in stochastic gradient, you still win over what Nick did. But in some cases you don't.
But the ratio between the top eigenvalue and the 10th biggest eigenvalue is like 4. So it's not that big.
Well, Nick had some good results on some problems like the CRF similar to that. It was not too bad.
Do you remember what the ratio was? Because
no, I think maybe Shunwi knows. No, you don't. So it's not a done deal, but it's possible. You know, it's clearly in the domain of the possible. Now you should see that this kind of issues they've not been studied seriously in the last 10 years. So there are things to do. There is no doubt. Yes?
This may be a question for my experience from machine learning is more from books rather than hands-on on the data. But could you say something about this other trade-off of the complexity of the model? Like it sort of increase the number of nodes in the network and take fewer steps.
I wish I could. It's so complicated. Like, suppose you do feature selection to reduce the number of nodes. Now the question is how much your accuracy decreases when you remove the features, and in which order do you remove the features? And that's so problem dependent. I'm not able to give general results there.
What I meant is you sort of don't need to get to the full minimum of your current neural net, but you could increase the model take, and you're stopping somewhere downhill, and that's giving you your regularization.
That you could. You can try it in practice and you see that in many cases it's going to work. The thing is that I'm not able to make a strict statement on that setup. But of course, if you have a practical problem, you should use it, of course.
Okay, let me rephrase the question. How often do you actually run to the minimum of your current model? How much is it the model itself, the neural net that gives you your regularization? How often is it just stopping early? Is it always stopping early?
Well, I'm arguing that even if you believe that the minimum is the right one, you should stop early anyway. Because there is no point computing that minimum with high accuracy anyway. Now you could do a little bit better because by stopping early, you can have early stopping effect and additional regularization effect that could be beneficial or not beneficial. So what I did here in all my examples, I had a separate regularization. And I was counting on this. I was trying to decouple the two problems because otherwise you don't understand what's going on.